but we're looking at this problem. This is a standard Charles log style problem. In which we use this equation here. You know, V1 over T1 is equal to V2 over T2. So we can calculate the volume, and we can calculate the temperature, given the other conditions here. In other words, volume over temperature is equal to constant, and so that ratio is fixed in the gas. So we go on, we solve this for V2. This is kind of funny because the book mentions about this. You know, one thing that we look at is this ratio. And so normally I don't write it like this. Let me show you how I write it. Normally I write it like this. So I would write it T2 over T1. Let's do it like this. And then it's taking longer to edit than I times V1. So when it's written like this, we have this little fraction in the front. And so we can see what happens. T1's our original temperature. V1's our original volume. So if T2 is bigger, you know, that makes this fraction greater than 1, which increases the volume. If T2 is smaller, then it's smaller. So, you know, this ratio, you know, between the temperatures will show what happens to the volume. So typically it's written like this. We get a T2 over T1 ratio. T2 increase, T2 decrease. Make sense? T2 increases, volume increases. T2 decreases, volume decreases. And then we continue on here with this. Okay. We need to save it. Again, T2 over T1 ratio. Then normally what I do is I go and calculate out the temperature so I can see, you know, the temperature, you know, when we look at the temperature here, the temperature decreased, right? We went from 65 to 22. And it looks like the temperature is less than half of the original. In fact, it looks more like a third of the original. But that's the Celsius temperature. When we look at the Kelvin temperature didn't change that much, you know. We add the 273. And so you might see a dramatic change in the Celsius temperature, but not that dramatic of a change in the Kelvin temperature. And so we don't see a huge change in the volume as a result of that. Well, anyway, the temperature decreases, which leads to a decreased volume. The temperature fraction. Now, this is why I was thinking, why did they write it like this? Because we called. You know what the temperature fraction is? temperature fraction is less than 1, this is the temperature. This is called the temperature fraction. So I don't know why they didn't write the equation like this. This is the temperature fraction. Temperature fraction is less than 1. That means T2 is smaller. Therefore, this fraction is going to be less than 1. That's what they're talking about there. We look at this as far as everything goes with these types of proportionalities. So the next one we're going to look at is, that was temperature and volume. But what happens with pressure and volume? So this is a movable bag, and we got some mercury there, so we can use gravity. The higher the mercury is, right, the greater the pressure. And so it's going to depend on the height of the mercury. And so if you want to increase the pressure, all we do is just raise this. It's going to increase the liquid pressure down here. If we want to decrease the pressure, we can lower this. In fact, we can lower this and create a vacuum, because if we keep lowering it, we lower it below the gas, it's going to create a vacuum. So we can get a vacuum, not a huge vacuum, but a vacuum. And anyway, here's the data. And so we take our observations, and so we can measure the pressure easily. How high is this column of mercury? Because what we're going to do is, remember, this. What does this look like to you? What this looks like to me is just a modified manometer. So here we could easily see the pressure of the gas here pushing on this side. What's pushing on this side? Well, we got this much mercury and atmospheric pressure. So that's what's pushing. And so it's like a manometer. This little deal. So we can easily measure the pressure and then see what impact that has on the volume. If we raise this up, it's going to compress this gas more. The volume's going to shrink. If we lower this down, it's going to put less pressure on this, and the volume's going to expand. And if we continue lowering it down, since this level is lower than this level, we can actually pull and expand it. Well, anyway, we take the data, and so this is a scientific method. This is what scientists do. They take observations, and then they do what? They do a process called patterns. It has a fancier name than just patterns and trends. What's a fancier name for patterns and trends? Did I tell you the fancier name for this? Books are written on this. It's called correlation. It's like correlation. What do you have? Data reduction. There's books written on data reduction. I was listening to a social science. So I guess the social scientists do the same thing. Because I was listening to a TED talk on one of these social scientists, and she said she throws all the observations, all the data on the floor, and then just stares at it, and then comes back the next day, stares at it until she starts to see some kinds of patterns develop, in the data, and goes on from there. So I thought, oh, that's interesting. This is kind of what we do, but we don't necessarily stare at it. We try to draw graphs. Other things. So here's the graph. Is that a linear graph or non-linear graph? This is non-linear. So this shows a non-linear behavior. But we have this, we can make predictions. So for example, we didn't take a data point here, but we can easily predict by interpolation, like is getting, or estimating where it would be between, or extrapolation beyond. But we don't want to do too much graphical interpolation or graphical extrapolation. We could draw the curve here and extrapolate it out. We'd like to fit this to a mathematical equation. That mathematical equation we call if we take our experimental data, our observations, and fit that to a mathematical equation, we call the mathematical equation a empirical equation, or a law. And this law is called Boyle's law. So what does a mathematical equation look like? Well, the mathematical equation is going to look kind of like this. Basically, it says the volume is inversely proportional to pressure. That's what this shows. Or, to make it equal, the volume is equal to the constant times the inverse of pressure. If we multiply both of these both sides of this equation by P, then we get this one. P times V is a constant. So in other words, this gives us, you know, we can plot the volume and it's inversely proportional to pressure. So let's go back. Or we plot the pressure. The pressure is inversely proportional to volume. So here's pressure, Y is equal to M, or not M, but some constant, divided by the volume. The constant is going to be used as a curve. Well, this is a very convenient form because, you know, this allows us to do predictions. For example, we don't actually have to graph that. You know, if you want to predict what the volume is or the pressure is going to be, you know, for any pressure-volume combination, we use this equation, the mathematical equation. And so we don't do any interpolation, we don't do any extrapolation, we don't do any graphing, we just plug it into the empirical equation that describes all that. And so anyway, this is the simplest form to use. It's P times V is equal to constant. Well, that means any combination of pressure and volume has to be the same constant. And so what we get is that we get this equation, which is very handy to have. It's P1 times V1 is equal to P2 times V2. So if we change the pressure or we change the volume, we can figure out what happens. Now, the way we write this is we're going to write this as either a pressure fraction or volume fraction to show how that changes. So let's see how they do this. And so typically we solve for P2 or V2. That's and so let me write. I'm not going to try to edit this. I'm just going to write it on the board. I just forgot my pen. Hopefully this pen works. Only red pen. Red pen. Well, anyway, if we're solving for P2, then P2 is equal to, okay, then we get the volume fraction, V1 over V2 times P1. And so take a look at what happens now. If the volume increases, what's going to happen to the pressure? And so we're going from V1 to V2. If the volume increases, V2 is bigger, then the volume fraction is going to be less than 1, therefore the pressure is going to decrease. If the volume decreases, then the volume fraction is going to be greater than 1, therefore the pressure increases. So this is what we talk. This is typically the way we visualize this. And the same thing with V2. If we're solving for V2, V2 is going to be based on the pressure fraction. Pressure fraction is going to be, well, V2 is equal to P1 over P2 times V1. So what happens to the volume here? Well, it's the same thing. If the pressure increases, the volume shrinks. If the pressure decreases, the volume expands. So let's try this problem now here. A gas sample occupies 5.18 liters at 774. Now, for temperature, the temperature always has to be in a certain unit. Whenever you use these gas laws, the temperature must be in Kelvin. But pressure need not, volume need not. You could use any volume. It could be gallons, milliliters, liters. Likewise, you can use any pressure. You just have to be consistent. So if you pick gallons, you got to stick with gallons. If you pick torr, you got to stick with torr. You know. And so we don't have to do any conversions. We'll just go straight off here because the pressures are consistent. They're in torr. So go ahead and figure out the volume of the gas or the pressure's increased. The pressure's increased, so the volume should decrease. guys get the answer? What do you get? 4.86. Okay, yeah, it's correct number of sig figs. We want 3 sig figs. Again, I want you to show me what we had before round off, which they don't. What was the drop digit?
0.
Okay, 4.860, thanks. Which rounds to 4.86. Good. Any questions on this? All right, so we did Charles' law and we did Boyle's law. You don't have to know the names, although, you know, Charles' law is he's the one who originally did the experiments, and Boyle originally did the experiments here. In fact, you don't even have to remember Charles' law and Boyle's law. It's nice to kind of register it, you know, to give them some credit here, Charles and Boyle's. But there are more. There's Gay-Lussac's and others, which Carpellicci ignores. And so Charles and Boyle's, yeah, you've heard it, and there are more, but we're not going to deal. Actually, in fact, you don't have to remember these because the law you should remember is this one. It's called the combined gas law. And so all you're going to do is you're going to combine Charles' law with Boyle's law into one equation. The way we do that is we'll just skip the math here and basically come down to this. It's just the pressure times the volume over the temperature is equal to a constant. And so this was Charles' law, V over T. This is Boyle's law, PV. And so we're going to get some new constant. That's all. But this ratio should be a constant, PV over T. And so the proper form of this is going to look like this. It's going to be P1 V1 over T1 is equal to P2 V2 over T2. This is the combined gas law. And this is the one you should remember all the time. And so we end up with two fractions. So if we use the combined gas law, it's going to look like this. Now, let's say we solve for P2. If we solve for P2, P2 is going to have two fractions. Like, for example, P2 is going to equal V1 over V2. That's the volume fraction. And then we'll have the temperature fraction, T2 over T1 times P1. So we can see what happens with the pressure. If the volume, let's say the volume increases, pressure should decrease. If the volume decreases, the pressure should increase. What about the temperature? If the temperature increases, so we're going T1 to T2, temperature increases, it gets bigger, then the pressure should increase, and if the temperature decreases, the pressure should decrease. So we can see what happens here. So what we have is we just have two fractions now, and we just plug in the numbers and we can figure out, you know, sometimes we can have like opposite effect. One does one thing, the other does an opposite effect, and so the change is actually minimized. Or maybe some, you know, they both go in the same direction for the change. So this is the combined gas law. Now, what I didn't mention earlier is this. There's a restriction on Charles' law, a mathematical or physical restriction on Charles' law. Go back to it. Charles' law says this constant pressure. What constant pressure means is that the pressure doesn't change. And so the pressure all the same. So actually, let me go back a little bit, because this is Charles' law is for temperature. And so if I'm looking at Charles' law, V2, let's say we're looking at Charles' law, we're solving for V2, or we could solve for T, or T2. This is Charles' law. So if we're solving Charles' law for V2, then V2 is, well, let me go back to the combined gas law here. You tell me. Okay, solve that equation for V2. So V2 is equal to what? Well, I would get V2 is equal to P1 over P2, right? And then T2 over T1. So I get the pressure fraction, the temperature fraction times the original volume, V1. Now, this is not Charles' law. This is the combined gas law. When we see Charles' law, well, let's go back to Charles' law. Charles' law, do you see that constant pressure? Well, constant pressure means is that the pressure doesn't change. So P2 is the same as P1. If P2 is the same as P1, then this is just equal to 1. And then we have Charles' law proper. And so for Charles' law to work, pressure must be constant. For Boyle's law to work, what must be constant? For Boyle's law to work, what must be constant is temperature. Temperature's got to be constant for Boyle's law to work. Otherwise, this doesn't drop out. We'd have to use the combined gas law. And so when we look at Boyle's law, there's a restriction. This happens a lot in science. In science, you can't just use an equation, a mathematical equation, with no regard to restrictions. There are restrictions on equations. That is, they're not always valid. You know, even though the math, you say, oh, the math is easy, you plug in the numbers, but you might get the wrong answer because you aren't paying attention to the restrictions on the equation. The restrictions, how do you know the restrictions on the equations? You have to memorize them because nobody tells you. And so if you're using the Charles law equation and the pressure is not constant, you're going to get the wrong answer. And so for Boyle's law, what do they say? Well, for Boyle's law, they say at constant temperature. So Boyle's law, we have to have constant temperature. If we had constant temperature, Boyle's law, that part falls off. All right, so let's do this one. So we only need one. You know, we don't need to know Charles. We don't need to know Boyle's. We don't need to know any of these. The only one we need to know is the combined, this one. All right, so let's try this one here. So the first step in doing these types of problems is you have to determine what P1, V1, and T1 are, and P2, V2, and T2. And then see what you're solving for. Now, pressure and volume can be any units, but temperature cannot. So keep that in mind. Combined gas law. PV over T is equal to constant. Let me know if you need a hint or getting stuck. Or if you have the answer, let me know if you got the answer. You have the answer.
I got
84.1 cubic centimeters? Is that what other people got? Is that the right number of sig figs? 84.11. You got 4 sig figs. Let me ask you this. How many sig figs are there in 21 degrees C? 2. Now the question is, shouldn't we have 2 sig figs in our answer, or 3 sig figs, or how many sig figs should we have in our answer? Yeah, okay. The correct answer is we should have 3 sig figs. Even though we have 2 sig figs in 21 and 2 sig figs in 95, we should have 3 sig figs in our answer. Why? And so the answer was that we have to convert it to Kelvin. So what difference does that make? Yeah, because addition and subtraction have a different set of rules. So when we apply the rules for addition, we end up with 3 sig figs. So we have 21 plus 273 is going to give us 294, which is 3 sig figs. 294 Kelvin. Let's take a look at the answer here. So first they label the variables, V1, V1, etc. We're looking for V2. Then we rearrange the equation. And so I wrote a little differently on the board. I wrote the fractions first. Let's plug in numbers. Right, 84.1. What was the drop digit? 1. 84.11, which rounds to 84.1. Yes. Okay, that's the combined gas law. This is important. Now, let me ask you this. We're pretty much nearing the end of the chapter here. Is our ultimate aim to get a law like this? Get a law like this, we can do calculations like this. Is that what we're after? Okay, in other words, does this law really give you a fundamental description of what's going on at the atomic or the particulate level here? You know, with this law, can we predict new laws? You know, new unforeseen laws? Maybe we could predict new patterns, I don't know. But ultimately, we really aren't after a law. Ultimately, we're after a theory, because from a theory, we should be able to derive all the equations from a theoretical starting point rather than an observational starting point. And so Charles' law, if we know the theory, we can easily derive that from theory or any of the other laws or new laws. And so law is not the ultimate goal. A law is very useful, though, because we don't have to really know what's going on. We can use it to make predictions, and making those predictions is very useful. All right, now we're going to go to some more jargon, some more vocabulary. When we're working with gases, there's something called STP. STP stands for standard temperature and pressure. Standard temperature for a gas is 0 degrees C, and standard pressure is 1 bar. And so sometimes what they'll do is they'll try to compare gases, different gases. When you compare gases, we want to compare gases at the same temperature and the same pressure. And so they pick 0 degrees C and 1 bar. 1 bar makes sense, because 1 bar is like normal, everyday pressure. But 0 degrees C does not make so much sense to me, because 0 degrees C is not so easy to work in. You know, I went to like a food warehouse today in the middle of the summer. This was out in what was this? This was near was 605 and 210 or somewhere around, no, 105, 605 and 105, around there. And it was all frozen food. And so these guys, you know, it's the middle of summer, it's baking hot outside, and these guys are dressed like they're in Antarctica, you know, like this, because they're working in freezers, and so, but they're in and out of the freezer. So 1 minute they're in, and it's super cold. The next minute they're out, it's super hot. And so we got to adjust to that again. But you know, I was thinking about STP, and I was thinking, you know, in order to work at STP, you need a lab that's temperature controlled, and you need that lab to be at 0 degrees C. And so when I picture a lab operating at STP, I always imagine these guys in these Antarctic suits going in and out of the lab. They walk out of the lab, it's baking hot. They walk in the lab, it's freezing cold. That's how I imagine it. And therefore, you know, when I was a Chem 4 student, I memorized STP. When I was taking Intro Chem. But do you know how many times since Intro Chem I've used STP? 0. But I cannot erase it from my memory. I want to erase it from my memory so I can memorize new things, but it's taking up space. And I have it so ingrained that I'll never forget it. What did I remember? This is what they tell you to remember. You know. Anyway, although when I was taking Intro Chem, it wasn't 1 bar. You know what it was when I was taking Intro Chem? The standard pressure was not 1 bar. The standard pressure was, at that time, what's close to a bar? Very close to a bar.